Hi, everybody. Welcome to our Thursday morning. I think everything seems to be working today. So today we're going to look at Module 7 and the initial greenhouse gas activity, which gives you some insight into how greenhouse gases work, what they are not. So this is the thing at the bottom of Blackboard here, so you can pull that up if you want to follow along. And this will address most of the objectives for this module, specifically the first four. It doesn't really talk much about climate change, more just about the chemistry of greenhouse gases. We'll use the IPCC references, and we'll talk next week more about climate change. Okay, so if you pull this thing up, you have this document, which you can go through to look at some facts about greenhouse gases. Now, the first thing we need to talk about when we talk about these gases is light. So the way that the greenhouse effect works is that radiation from the sun hits the earth, and then some of that radiation is absorbed. When we say radiation, I should define that also. We're talking about all electromagnetic radiation. So that's everything from the super high energy gamma rays to really low energy radio waves. If you click this first link, it'll bring you to this NASA reference on the electromagnetic spectrum. So this shows you all the different kinds of light that there are and some of the uses for them. So really long wavelength, low energy, low frequency light is what we call often radio waves. That is a type of light when radios transmit, broadcast things, and then you can receive those using some sort of a receiver like a radio. Then as we go to slightly higher energy, we have microwaves, which are used for communication. Our cell phones run primarily on microwave frequencies, as does your microwave oven, which excites molecules in the food to create heat. But the word microwave actually just refers to a portion of the electromagnetic spectrum. Then going a little bit higher in energy, we have infrared light. So this is like the light that comes out of your TV remote. Kind of a fun thing you can try. I don't have a remote here, but if you use your cell phone camera, you can actually pick up infrared light sometimes. So if you put your camera on and then you put a TV remote in back of it and push the buttons, you'll see the flashing lights that you don't normally see. That's because our eyes don't see infrared light, but the CCD in the phone can do it. So the thing that takes pictures can see that. So that's infrared light. That's also what we call or what we see when we think about things like night vision. If it's dark and you don't use a visible light source, you can use an infrared light source and you can see the infrared light being reflected back. You can also do this. So infrared light is also a way that heat is transmitted. So anything that is that has energy in it, that has potential energy, is transmitting that energy via infrared light, which is why you see sometimes those plots of heat signatures where you can see like a body giving off light in the dark, and that's because it's giving off infrared light. You can also experience this like if you're near a fire. Even if you're not right close up to the fire, if you look at the fire, you turn your face toward the fire, it's going to be hotter than turning your face away. And that's because of the infrared light coming out of the fire toward your face. So when a heat source, whether it's a fire or a heater or whatever, is giving off heat, it's not just heating the air around it and then that air is mixing with other air and heating the room. That is also happening. That's called conduction or convection heat. But there's also directly infrared light coming out of that and heating everything that it hits. And so that's what's going to be important for our greenhouse effect. Now, just to finish up our spectrum here, higher energy light, we have visible light. So this is the spectrum that we can see with our eyes. And that's that visible radiation. Then above the visible spectrum, which we can't see, but it's higher energy, we have ultraviolet light, and then X-rays and gamma rays, cosmic rays, things like that we don't deal with quite as much. We can't see those. As you might know, these higher energy lights are ones that we tend to be cautioned against. That's because those types of light involves something called ionizing radiation, which is radiation that is strong enough to knock electrons off of things. And so, for example, ultraviolet light from the sun, of course, if it hits your skin, that's bad for your skin because it's damaging it with this high energy. It can knock electrons off, which can mess with your DNA and ultimately cause cancer. Excuse me. So that's why we protect ourselves from those higher energy lights. When you get an X-ray, they shield you with lead so that the rest of your body isn't getting exposed to the X-rays. If you have to get chest X-rays, things like that, they will keep track of that because you don't want to get too many of those types of X-rays in a short period of time because of the buildup of damage from that radiation. Normal, once in a while kind of thing is fine. All right, so let's get back to our infrared light here. So the greenhouse effect is the light of all different radiation, all different energy levels comes in from the sun, hits the earth, and then some of that energy is absorbed and some of it is reflected at a lower energy, which is infrared light. That infrared light, in turn, is absorbed by the gases in the atmosphere, the greenhouse gases, which are predominantly carbon dioxide, but also water vapor, methane, nitrous oxide, and a few others. And those molecules absorb that infrared light and then reflect it back to the earth. So rather than the heat escaping, the heat is held in the earth. And that's why Earth can have like a temperate climate that supports life, as opposed to other planets like the moon, for example, which doesn't have an atmosphere. So that's still getting bombarded with just as much radiation from the sun, but it doesn't have this kind of reflective feedback effect that keeps the heat in the earth. So the greenhouse effect is a good thing. It's something that allows us to all survive. The problem is when too many of these gases or too much of these greenhouse gases end up in the atmosphere, they're reflecting and holding more and more and more heat, which is causing the earth to heat up over time. So that's what's causing global climate change. That's the problem. The greenhouse effect in itself is a good thing. It's when there's too much of it that we start having these temperature problems. All right, so how do molecules absorb infrared light? You can read in these couple references about how that works. I'm going to show you the one simulation here. So you can launch this visualization, and let me talk about how that works. So I have to switch here. All right, I think that looks good. All right, so here's our simulation. So what we're seeing here is a graph. On the x-axis is the most important part here. These are energies, and they're plotted in a little bit unusual way of plotting energy, a unit called wave numbers. So the lower energy is actually on the right, and the higher energy is to the left. So rather than starting at 0, we're starting at 4,000, and we're going down in energy. That's just kind of the traditional way that this has been done. And so what we can do is we can click on various molecules here and see how they absorb infrared light. The y-axis is the intensity of light that is passing through the sample. So imagine you have a container full of this, whichever of these gases. We'll start with carbon dioxide. Okay. And so what we're seeing here is, imagine you had a container of carbon dioxide and you pass infrared light through the carbon dioxide of all different wavelengths, and you're measuring to see which wavelengths or which energies get through and which ones get absorbed. So if the energy gets all the way through, doesn't get absorbed at all, then it ends up top here. So that's like these energies here, we're saying they don't get absorbed at all by the carbon dioxide. They just pass straight through. But these energies here, where we see these things drop down, we call them peaks, but I guess they're really valleys. These things coming down are showing absorbance or absorption from these molecules. So you're seeing that at these particular energies, carbon dioxide is absorbing the infrared light. And it's actually at this really low end of the spectrum here where we have this greenhouse effect of the light that's being absorbed. So what you can look at is each of these molecules, you can see if they are a greenhouse gas or not by whether or not they absorb infrared light. And any one that has a spectrum that has these values would be considered a greenhouse gas. Excuse me. So it would be considered one that, so this is methane, for example. You can see a lot of absorbance there. So those are greenhouse gases. One thing this simulation doesn't have is a comparison with molecules that do not absorb infrared light. So these are all of these are greenhouse gases because of their absorption, some more so than others. But if we had a molecule such as oxygen, O2, or nitrogen, N2, that does not absorb infrared light and is not a greenhouse gas, you would instead just see a straight line going all the way across. So there would be no dips or any of this stuff that we see here. Maybe most obvious with the carbon dioxide, these big peaks coming down. You just see a straight line all the way across, indicating that that molecule is not absorbing any infrared light. So there's a few questions on the sheet that you can answer about that. If we go back here, back to Blackboard. So work through those. There's also a nice explanation in this link chapter here about how infrared light is absorbed by molecules and what that has to do with the greenhouse effect. And then you can compare it to the spectrum from bromine, which is an example of well, you can see we didn't talk about bromine, but you should be able to look at the infrared spectrum and determine whether or not bromine would be a greenhouse gas. All right. So once you work through that stuff, you should be able to explain what it is that makes a gas a greenhouse gas. And then you can move on to the next page. Now, the next page gives you a couple things to do. One is to practice balancing chemical equations. So you may need to look up some references if you haven't done this before on how to balance a chemical equation. And then it's going to ask you to translate these sentences that describe various processes into balanced chemical equations. So for the first one, we've got during respiration by plants and animals, a carbohydrate reacts with oxygen to produce water and carbon dioxide. So you're going to write, you're going to first figure out what types of chemicals are we starting from. Those are going to be our reactants on the left side of the equation. And then what types of chemicals are we producing? Those are our products on the right side of the equation. So in this case, we're saying that the carbohydrate glucose, C6H12O6, reacts with oxygen. So those are the things that are doing the reacting. Those are going to be on the left side of the equation. And then water and carbon dioxide are produced. Those are on the right side of the equation. So we'll write C6H12O6 plus O2, and then give the arrow, and then H2O for water, and CO2 for carbon dioxide. Then we have to balance that equation. And if you haven't done that before, again, it's not real difficult. There's kind of a process to it. I have some videos on my channel you can look at for that, or just other references if you prefer. And you can balance the equation. So then there's a couple other parts that apply more to this idea of greenhouse gases. So first, identify the greenhouse gases involved. So this might mean, again, looking up some IR spectra, but I'll tell you for the first one, the greenhouse gases involved in this equation are water and carbon dioxide. All right, those are both greenhouse gases. And so then we want to say, is this a source or a sink for the greenhouse gas? So what that means is a source is a process that produces the gas, and a sink is a process that gets rid of or absorbs the gas. In this case, we're producing our greenhouse gases, we're producing water, we're producing carbon dioxide. And so that means that this process is a source of the greenhouse gases. And then the third question is, if it's a source, is this anthropogenic? Is it something that humans do? Or is it just naturally occurring in the world? And so for respiration, since that is something, I guess, that humans do, but it's something that everybody does, including plants. So I would say that is probably a natural process, right? Anything that exists in the world, any living thing, is going to undergo respiration and do this process. So what's an example of an anthropogenic or human process? If we go down here, like number 5 is pretty clear. Combustion of fossil fuels. That's something that we're doing as humans, not something that just naturally occurs. So we would say that is an anthropogenic source of greenhouse gases. All right, so that's a good intro to the chemistry of greenhouse gases, and working through this activity will help you to get that into your brain a little bit more. If you have some other references or some other ways that you've found to figure that stuff out, as usual, you're welcome to use those as well. Just report on your module reflection what you've done. And I will see you next week when we'll talk more about the effects of greenhouse gases, which is what happens when too much of the greenhouse gases get in the atmosphere, and that is global climate change. So I will see you in Wednesday in lab. As usual, let me know if you have any questions. See you next week.